All right, so here's the difference. We've done linear inequalities. Now we're going to do systems of linear inequalities, and you will see why this is so easy. Are y'all sure we did that with the shading? Okay. All right. So here's what we're doing. If I've got, remember, oh yeah, we did because we picked a point. If I have, for instance, this equation, maybe a solid line that shades down here. The difference in one inequality and a system of inequalities is that the system is made up of multiple inequalities. So what we're going to do is we're going to graph each inequality, and maybe this one comes through like this as a dashed line and shades down, and maybe I have one more that comes as a solid line here and shades up. And so I'm graphing more than one inequality on the same graph. And the reason I told you the colored pencils might be handy is because this time, remember with linear equations, the systems, I'm looking for where they cross, what they have in common, what they share, that one point. With inequalities, what I'm looking for is the total area that they share, okay? So if you look, where all three colors overlap, I'm going to do this a little bit in a...
It's like a triangle.
It is like a triangle. Shh, guys. So if you notice, I have this triangle in the middle.
Yeah. That's the...
And it's bounded. It's bounded on two of its three sides with a solid line. And it's bounded on one of its sides with a dashed line. What does that mean with the dashed line there?
It can't go to the...
It can't include that, right? So it does not include that. Now, here's a couple things you need to know. Thing one. This shading, that triangle, is what we call a feasible region. Okay? Feasible region just means the solution area. Okay?
I respect that.
A lot of times our solution areas, okay, have these endpoints here. What do you call these little points on a triangle?
Corners.
Vertices. Somebody said vertexes, but vertices, these are still your vertex, your vertices of your feasible region. And this is going to be very important whenever we get to the next section where we're doing linear programming, because we're actually going to have to calculate those values of those vertices. But for right now, we're just looking that we know that those are vertices. Now, this is what we call a bounded system. And the reason it's bounded is there is no place that it goes off forever and ever, right? It is something is keeping it in a certain area.
Yeah.
If that bottom green line was not there, then it would go forever and ever down, and it would be an unbounded region. Okay? So if it's completely closed into a certain shape, it's bounded. If it's not and it goes on forever, it's what we call unbounded.
We have a lot of them with more than two.
So if it's
like
got
two equations. It's like...
Yeah, sometimes.
If it's got any dash, it's unbounded.
No, if it's got, hold on and I'll show you an example of an unbounded.
An unbounded would be, you have to have two, wouldn't you? You don't have to.
It just depends on how they intersect and how they go.
So what if you have two parallel lines and then one running through?
Well, you could have, in fact, I'm fixing to do one with two parallel lines, but they're shaded in opposite directions instead of the same. So
then it'd be this or this.
All right. Y'all got it?
Yeah, we got that.
All right, let's do a couple together, because actually let me set up a couple other scenarios for you and show you. So that's a bounded. and then we'll actually go through graphing. Let's say that I have something. Here's my graph. This one shades up. Yeah. I'm going to actually work through some examples, but I want to show you. Yeah.
And I have the clothes tonight. Oh my God. Yay.
All right, guys, there's a lot of chitter chatter. I need y'all with me. That's 2 lines. I'm not actually graphing the inequalities just yet. Right now, we just want to run you through what they look like when you graph them. Then we'll actually do it. This one would be, look at my feasible region. From here to here, right? But do you see that there's nothing keeping it from going on forever to the left? Does everybody see that? So this is what we call unbounded. Okay? There's nothing keeping it from going on and on and on forever to the left, so that's an unbounded system. Does that make sense, how we're bounding and unbounding? One more kind. Yeah, we're gonna actually work through an example of each of these where we actually graph it and show what it looks like.
Those are all. But there's no triangle.
So
it's not bounded. It's unbounded.
No triangle.
And it doesn't, listen, some of them we will graph so many inequalities that maybe the solution area looks something like
that.
this.
Okay.
Because if you look, this would be 1, 2, 3, 4, 5. Okay? And we will get to some like that. So I just want you to, it doesn't always have to be a triangle is what I'm getting at. Okay? But that's why your colored pencils are really going to help you to see. If you don't have colored pencils, sometimes I'll do like dots here, squiggles in another, some kind of design in each one, and then where do all the designs overlap?
When we're like shading, we need to shade the others before we shade the balance or like the.
Yeah. Guys. Last one that I want to show you before we actually do them.
There's only one vertex on that one, right?
That is correct.
Good knowledge.
That is correct. There's only one vertex there. If I had 2 parallel lines, and this is kind of, I think this is what Dylan was asking a minute ago. Let's say one of them I shaded up, and the other one I shaded down. Remember, when you're looking for solutions to systems of any kind, you're looking for what they have in common and what they share. So as you look at this one, what do you notice?
It has nothing in common.
Nothing in common. This is a no solution set at all for this one. They have nothing in common, so there's no. So remember, if they were parallel lines that never touched, it was no solution.
I thought it would be like, it has to be this or this.
No, this one's going to be no, because you're only looking at what they share. Now, if this,
What, like, isn't there one that would be an answer, like, that has to be a certain thing?
we'll get to a couple and or ors, but not yet. Not here.
Wait, what if it's shaded like, let's just
Like
say
that?
it's a triangle, but it's shaded outside of the triangle? There'd still be.
You could. If it's shaded outside of the triangle, if the feasible region is outside and it goes on forever in any direction, it's unbounded.
Okay, but if you shaded that parallel down, if you shaded that parallel line down, then it would go to under the set.
Correct. So now my solution area is only above the solid line there. Does everybody see the difference? See what we're doing? Those are unbounded also. All right, let's just do it. I was just saying if it switched from going below it to above it, this changes that now this is the feasible region above.
Wait, so that's unbound?
Unbounded, yeah.
So the no solution is
No solution, yeah. All right, so let's run through. I just wanted to make sure that I showed you what each scenario looked like, so if you encounter it, you go, oh yeah, we talked about that. This means da da da. All right, so let's run through a solution. We will, but not just yet. All right, so here you will see why I spent so long and really got you to graph by hand. your lines. Because if you can't graph a line, you can't graph a linear inequality, okay? And this we're using strictly by hand and not the calculator, so we got to be pretty precise here. All right, so what we do, we start with these by graphing each one. I would graph each one in a different color. Let me put my... Let me put my grid on here.
I'm gonna graph this thing, graph it up, negative 4.
All right, so things to keep in mind. Things to keep in mind are solid or dashed and which way we're shading. I'm going to start with a pink here at the beginning. I'll let this one be pink. This is going to be a dashed line, right? Because it is not or equal to. It is just greater than. All right? My y-intercept, these are nice because they're in slope-intercept form, which is an easy way to graph. So my y-intercept here is what?
For which one?
-4. We're looking just the first one, -4. 1, 2, 3, and 4.
Oh, no, it's just be a dash line. Dang it.
Yeah, it's got to be a dashed line.
Well, I know it's be dash, I wrote it. I don't know how to fix that.
All right. The slope is what? 2 over 1, which means do what? Close. Up 2 over 1. Is that what you said? I thought you said over 2 up
I
1.
wrote to the side, dash.
You're doing it right, but you're saying it wrong. All right.
This one's gonna go way off.
All right. Should I shade above or below?
Above.
No, is it negative?
It's above, but
Above.
it's
Y is greater than, so I want to shade the direction that Y gets bigger. Y gets bigger above. If you don't understand that, by all means, plug a point in. No, you're not dumb. Plug a point in.
You can still get 0, 0, right?
All right. Yes, you can still do 0, 0. All right, second equation is going to be blue, and it's going to be a solid line because it's or equal to.
I don't have any tools.
All right, this time, what is my y-intercept? 3. 1, 2, and 3. Slope is what? -0.5, down 1 over 2. So down 1 over 1, 2. Down 1 over 1, 2. I should really get my line drawer.
No.
I was counting as I did.
Okay.
Should I shade above or below? It's greater, yeah.
Above. Hey, it's above.
It's above. If you plug in 0, 0, yeah,
0, 0 is not right.
it's not right, so don't plug where 0, 0 is. Plug
Oh,
in.
you're right.
Shh, 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 shh. What?
Oh, wait, are you doing like 1 over 2?
Yes, I went down 1, right 2.
So then that little triangle at the top.
So now, look at my little unbounded triangle here. I have a dashed line here. I have a solid line here. They meet at this point. All of this is my feasible region. Is it bounded or unbounded?
Unbounded.
That is unbounded. Why is it unbounded?
There's a dotted side.
It goes on forever and ever up at the top, right? Does that make sense? Okay.
Unbounded because it's not bounded.
Unbounded because it goes, yes, there's nothing holding it in a certain spot. It goes on forever. All
So
right.
you can fix it.
Dude, number 1.
This is going to be an easy one, and then we'll do a couple a little more difficult. Let's do this. Let's graph the system.
All right.
Y is greater than or equal to x plus 5. Y is less than x minus 4.
So that one's gonna be
Plus 5.
Yeah, plus 5. Dash, green and solid here, and I'm going to do
yellow, that's what I'm doing.
No degree.
yellow and dashed here. They're parallel, and hopefully you saw that at the very beginning. What would clue me in that those two lines are parallel?
Same slope.
They have the same slope, right? So automatically I know these are going to be parallel lines. I'm going to do the bottom one first since I'm still in. Y'all go ahead and try it while I'm doing it as well. Somebody already got it.
I don't think I got it right.
Got him. Now you're in what I was in on that last problem.
Wait, I can hear you. Up one, over one. Go. Up one, over one.
I just wrote every mine was black.
That's what I'll say. So if you want to go back and follow along, because we're gonna actually write the equation, the inequalities ourselves. So this is on page 53. It's example number 3. Somebody said, "You're gonna do a real world one, aren't you?" Yes, we're gonna do an application problem where we have to write the inequalities, graph the inequalities, then find the solution area and interpret what that means. Okay. All right. Chelsea has final exams in calculus, physics, and history. She has to spend 25 hours to study for the exams. Okay, okay, there we go. All right, she needs to spend, let me write down what she's got. She's got, what did I say? Calculus, physics, ooh, Stacy. Physics and history that combined, she needs to spend 25 hours to study. She plans to study history for 2 hours. She needs to spend at least 7 hours for calculus. So that's greater than or equal to 7, right? At least 7. And over 14 is too much. She hopes to spend between 8 and 12 hours on physics.
I barely studied.
Oh my goodness. Write and graph
This right here would be a question mark one.
a system of inequalities to represent. All right.
That's on you.
So she already knows that she's studying 2 hours for history, so I can take that out, okay?
So we put
There's no varying on that. She's studying 2 hours. So really what I'm looking at is calculus and physics for a combined total of how many hours?
23.
23, right? Because we're taking this 2 hours out, so we're going to say for 23 hours. Do we all agree with
And the
that?
question is, how many hours does she spend on each?
So what are the possible number of hours that she could spend on each one, all right?
Okay.
So if I add the number of calculus hours to the number of physics hours, it's got to be what?
23.
Or less. She's saying she hopes to spend that much, right? So I'm going to say it's got to be less than or equal to 23. She can't spend any more than that, right? Remember, we're talking inequalities here. She draws the line. Yep, that's it. That's bottom line.
Yeah, let's fit up.
Whole day.
All right, this one looks harder than what it is once you get it because they're all simple, simple, simple. All right, calculus has got to be between 7 and 14.
7 plus 14.
I don't
How do you say between?
See the middle.
7 something something.
So this is the or.
Okay, between those two values. These are going to be a lot of straight line functions at the end of the day. And then physics has got to be between what?
8 and 12.
8 and 12. We're going to say, she said no more than 14, so she can spin up to 14. So we're going to put a line under that. All right, so let's think about what this looks like on a graph. Again, we're a real life problem. So really, we're looking at first quadrant because you can't spend negative 2 hours. I don't know. Some of us, no, I'm just picking. We don't spend negative 2 hours studying for anything. Yeah. So we're going to be first quadrant. So I'm just going to focus mainly on the first quadrant here, okay? They are. They're all solid lines. And with the exception of this equation, they're vertical or horizontal lines, so it makes it a little bit easier, okay? So,
How do we?
Yeah, so you're going to need it. So what I want to do really is I want to decide which one's independent, which one's dependent. In other words, which one's going to be X and which one's going to be Y. Since it's just written C first, I would do X is C and P is Y. So let me just set this up now with my new variables. X plus Y is less than or equal to 23. And then between 7 and 14. 7 and 14 for calculus, is that right?
Mm-hmm.
7 and 14 for calculus, and then between 8 and 12 for physics. All right, I'm going to go ahead and set up my first quadrant here. These are all solid, yes. What is going on?
All solid. Let me blue, green, and red.
Yeah, let's do white.
All right. This is my physics that we let be Y. Calculus is on the bottom down here. We'll just put a C because I can't. All right. I might have to go by 2s on here. I don't know if I can go all the way to. Almost. I'm going to redo it.
How far down?
Are y'all picking on me?
How far down?
No, we're not.
All right. Well, okay, so what I'm looking at is I know because this is in standard form, my X and my Y intercepts are both 23. I'm going to go by 2s so I don't have to redo my graph.
You'll have 5.
Okay, but that's going to be hard whenever I get to my. I'm going to go by 2s.
I wrote mine in 2s, please.
I'm going to go by 2s. All right. 2, 4, 6, 8. You don't have to go by what I go by. 10, 12, 14, 16, 18, 20, 22. So halfway in between at 23 here. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 23.
3. Okay.
Okay.
Oh, I gotta get the other one, 3.
I'm gonna have to interrupt another one of my graph.
Interrupt them, Luke. I'm sure they won't mind. All right. All right, I am right here. I am now in a triangle, and I am bounded technically here because, again, we said we can't study negative 3 hours. Although some of us may try. 23 on X and Y. If you use cover up when graph, both the intercepts are 23. Now, if you think about what this means, X has got to always be between 7 and 14, in the middle of them. Well, X equals is a vertical line, right? So I'm going to go between 7, 2, 4, 6, 7. 8, 10, 12, and 14.
Oh, it's not.
Now look,
Wait, where are your points at? 7, 14?
That's something else right there. That is-
yeah. All right. X has always got to be between 7 and 14. So no matter where else I am, X needs to be between these two values. Because X equals is a vertical line, then on either side. And if it confuses you to think about it, then think about this. This is the same thing as X is greater than or equal to 7 and X is less than or equal to 14. And you could graph both of those. Okay, X equals is a vertical line. And they would overlap right here in the middle.
Oh, we're just drawing.
You don't get
Wait,
it
why
now?
do we put signs?
No.
Well, remember that alligator mouth needs to always eat the same thing. So if you split it up, then X is bigger than 7. And if you split it up this way, X is less than 14.
Then we do the same thing for Y.
She do the same thing for Y, but I'm not vertical this time. I'm
You're
horizontal, right?
you're a hot dog. Yeah.
What?
Landscape.
Okay, between 8 and 12. So 2, 4, 6, 8,
I don't even know what color.
10, 12. Now, if you did these as two separate ones, you'd need a whole bunch of colors. All right, so I am between I'm solid because it's or equal to. I think these are fun.
I hate these.
Well, these are the ones that you think my brain hurt at night. Oh.
Now look at my feasible region.
Why'd you try to sign on that edge?
Well, because when you split them up, that alligator mouth still needs to eat the X.
Oh, shoot, I
See what I'm
didn't
saying?
think it was a green line.
So,
Oh, yeah, you're right. Yeah.
Hey, we need that.
all right, now look, be very careful here. Look at this region. You don't understand? Y equals a number is a horizontal line.
That's a weird shape.
All right, now listen. This is definitely not as hard as it gets.
I mean, I can do the graph and you can
I need you to really work on being precise, as precise as you can on these, because we need to calculate the vertices of the feasible region that's made, okay? Now, I'm gonna save that for tomorrow when we do the linear optimization, even though it pops up in this section.
I mean, I can get it right.
Because here's what's gonna happen is your lines, these are easy because the lines are vertical and horizontal, but as these lines start coming in diagonal, you have to solve sometimes a system of linear equations to find that point, okay? Really, and that's why I focused on the calculator the second day on the system of equations, because I want you to be able to go in there and find the intersection point, okay? Now, understand what this means, okay? This means that any point in this box, pick a point in this box, any point. 4, 6, 10.
6, 10.
Here's 10, 10. I heard that first, so I'll go with that. 10, 10. That means she could spend 10 hours on calculus and 10 hours on physics and still satisfy all the requirements that we set up. Any point in that box or on the outer realms of that box satisfy those requirements. Does that make sense to you? Okay, let me give you your homework.